Hey y'all, it's Mr. Boyden back at it again, and today we're going to talk about law of sines. We're shifting gears a little bit at this point in the unit. The first half was really theoretical, and the second half is going to be all about how we can use trigonometry to solve triangles. We learned back in geometry that you can use SOHCAHTOA and trigonometry to solve right triangles, but today we're going to see how do you extend trigonometry to triangles which are not right triangles, namely any Euclidean triangle, as I'm calling it here. Okay. The first way is going to be with the law of sines, and that's stated right here. So if you're taking notes, you're going to want to write that down. Please note that in the numerator we have uppercase letters, so sine of big A, big B, and big C. The significance of that is that these are each angles. In the denominators, we have little letters, little a, little b, little c. The significance of this is that these are side lengths. Okay, and then let's compare that to the diagram. Now, if you don't already know, when we label up a triangle, we have to label an angle and its opposite side with the same letters. So big A is the angle, little a is the opposite side, big B is an angle, little b is its opposite side, big C is an angle, little c is its opposite side. So the law of sines is useful in what cases? Well, note this. We're only going to use two chunks at a time. It doesn't matter which two chunks you pick. See, there's 1, 2, 3 sections of this. So it doesn't matter which ones you pick, but recognize that sine A and A go together. So you'd need something and its opposite. And sine B and B go together. You'd need an angle and its opposite. So that's what we're going to look for that's going to tell us that it's a law of sines question. Something and its opposite that's labeled. Let's get into seeing some examples so you can see how it works. Here we're asked to find all the missing side lengths. So what I'm going to do is I'm going to look for an angle and its opposite and another angle and its opposite. So I can see 50 and 12 are opposite. I'm going to use those. I see 35 is opposite from B, and so B is what I'm going to find. Now, what I'd want you to do is start by first writing the thing that you're trying to find. I'm trying to find B, so I'm going to write that first, little b. And we're going to notice that it is paired with its opposite side, so we're going to say sine of 35. And that's going to equal, now I've chosen to put a side length on top, and I'm allowed to do that as long as I'm consistent with all the fractions. So now when I go to this second fraction, I have to also put a side length, so I'm going to use 12. And 12 is across from 50, so that's going to be sine of 50. And I want to get b by itself, so all I have to do is multiply up the sine 35 onto this side. And then I'm ready to type this in the calculator. And I've actually brought along my calculator today on the screen, so I'm going to go ahead and type this in now. Oops, because I went to a graph screen. So calculate. All right, let's see. 12 sine 35. And then we'll divide by sine 50. Kind of hard to see, but looks like that's 8.985. I'm going to call that 8.99. And that's little b. We were asked for all missing side lengths, so let's also consider finding side C. So for that, I'm going to start with C, and I'm going to divide by sine of, angle C. So I'll need to find that. So what I'm going to remember is every triangle, at least a Euclidean triangle, has 180 degrees as an interior angle sum. So we'll just come over here and we'll do 180 minus 50 minus 35. And so we find out that this is a 95-degree angle. So that'd be sine of 95. And then I'm not going to use 8.99 here because 8.99 was a rounded answer. 12 is an exact answer. So I'm going to use 12 over sine 50. Multiply up the sine 95. And again, it's calculator time. Oops, I meant to cross that out. So I'm going to go ahead and type it in. So 12 sine 95 divide by sine 50 and 15.6. One thing that we should get in the habit of doing is making sure our answers are reasonable. Now, there's nothing here that says that this triangle is drawn to scale, but here's something we should remember from geometry. In a triangle, the smallest side will always be opposite the smallest angle. We found the smallest side was B. Let's double check. Is B opposite the smallest angle? Yes, it is. Similarly, the largest side, which we're saying is C at 15, is always opposite the largest angle. which holds up here. That's 95. So these answers are reasonable. Let's try another example. This time we're not given a visual, so one of the best ways to proceed is to actually just make our own. In a triangle, we have angle A, and angle B. So we have to be a little bit careful with how we draw this. I'm going to try my best to put in sort of a 25-degree angle. So 25 degrees. They told us that one of the side lengths was 4. So maybe I'll say this is 4. And they tell us another one is 3. So actually I'm going to zoom in here just a little bit so it's easier to see this. All right, so we have to be really careful with how we draw that other side because we don't actually know if 3 comes back like this or if 3 goes down like that. So you see how there's actually 2 different possible triangles here for this setup? So we'll have to be a little bit careful. I'm going to come over here and do my best to draw each. So one of them is an obtuse triangle. Oops, I'm going to try to draw it again. Try to draw it a little bit bigger, maybe a little better. So there's the obtuse triangle with 25 there. Remember, big A and little a are across from each other. 3 and 4. And then we also have an acute triangle, and that's the one that goes out like this. Or though I'm not sure it's acute, but it looks like maybe it's acute. And then similar labeling, so 25, 4, and 3. Now, that gets a little bit confusing because how do we know which is which? And when we start doing our setup, how do we know which one we're solving for? Well, I'll show you here in just a second. Let's try to do our setup. It's going to be basically the same setup either way because all I can find right now, I have 4. I'm going to need that angle opposite, whatever that angle down here is. We can see this one's acute and that one's obtuse. I don't know what that is. I'm just going to call it, well, I guess I'm going to have to call it B because 4 is little b. So let's do our setup. I'm going to be looking for sine of big B. We're going to divide that by 4. Over here, sine of 25 divided by 3. I'm going to multiply up the 4 up to here. And then here's where a lot of people make a mistake. If you type this in the calculator, you will get an answer, but it won't make any sense because there's a sine sitting right here. So we have to get rid of that sine by doing a sine inverse. Remember, inverses find angles. So anytime you're looking for an angle, you're going to have to use some sort of an inverse trig function when we're doing trigonometry. So we have to type in sine inverse of 4 sine 25 over 3. All right, to the calculator. So watch how I do this. If you have an Inspire, I think this will be helpful. I'll show you some tricks here. Okay, so I go into my menu. I'm going to go sine inverse. Once I get into sine inverse, notice right above the divide button, you can actually make a fraction. So then in the top part, all I have to do is type in 4 sine 25. And then I'm just going to press the down arrow here to get down into the denominator. And I'll hit a 3. And hopefully that's going to work. 34.3 degrees. Yep, cool. So then the question is, what did I just find? Well, that's an obtuse angle. I probably didn't find that. I think I found this one. So 34.3. Okay, so let's take a minute. Let's just finish up this triangle on the left, and then we'll talk about how to figure out the triangle on the right. So on the left, what I could do is I could do 180 minus that answer I just found, 34.3, minus 25, and we'll find the missing angle. So it rounds to 120.7. So 120.7. And then we need to find this missing side length down here. And if that was A and that's C, I guess this is little c. So little c over sine of 120.7 equals, and I'm going to use 3 and 25 again. So that would be 3 over sine 25. Let's multiply this guy up. And calculator time it is. So I'm typing in 3 sine 120.7 divide by sine 25. And I'm getting 6.1 when I do that. And that makes sense, actually, because now I'm saying my biggest side is across from my biggest angle. Okay, so this part of the triangle is done. So what the heck? Why did the calculator spit out the angle in the triangle on the left instead of the triangle on the right? Well, here's what's happening. When we type in all this stuff, and I'm talking this stuff right here, when we type that in the calculator, what your calculator functionally is figuring out is the first spot on the unit circle where that's true. And so what it does is it's looking for whatever that value is, this 4 sine 25 over 3, it's thinking of that as a y value. It's looking for a place on the unit circle where that y value is achieved, and it's finding it right there at 34.3. So what we get to ask is, were there any other places on the unit circle where the sine value would be the same? Well, sure. How about right over here? Think of like the same y value going across the other way. And we would know that this right here is also 34.3 degrees. So what is the angle that describes that spot? Well, all we have to do then, we have to do 180 minus 34.3. Because remember, on the unit circle, we'd be saying that this over here is 180, so we're going backward by 34.3. So that's 145.7. Which means this angle right here is 145.7. Okay, now, guys, I'm going to skip the rest of the example because it would go exactly the same as what we just showed on the left, okay? All we would do is we'd find this missing angle, we'd set up law of sines to find that missing side length. So we call this the ambiguous case of the law of sines, and it's probably the most confusing thing about the law of sines. Process-wise, law of sines isn't real bad, but this is one of those things that can kind of jump out and bite us if we're not careful. So look out for the ambiguous case when you're drawing your diagrams. Now let's try everybody's favorite, the famous story problem. Airplane spots an island in the distance. It sees the close side of the island at an angle of depression of 39 degrees and measures with a rangefinder that it's 1,200 feet from that spot. It can see the far side of the island at an angle of depression of 27. How wide is the island? All right, let's practice drawing the picture. An airplane spots an island in the distance. Let's assume that airplane's in the air. That seems like a logical place for an airplane to see islands from. So I'm going to draw my island. Island is going to be flat in this case because it doesn't say otherwise, and why would I make it harder than I need to? I'm going to put my airplane up here because it's spotting it off in the distance. It sees the close side of the island, so close side of the island, at an angle of depression, remember that's in reference to horizontal, of 39 degrees, and measures with the rangefinder, it's 1,200 feet from that spot. It can see the far side of the island at an angle of depression of 27 degrees. How wide is the island? All right, guys, so here's where people get a little bit confused. If we look at this as just a triangle, and we label what we know, we don't actually know that much. We know that this is x, and we know that this is 1,200. Unless we're crafty, we don't actually know any of the angles inside the triangle, because 39 isn't inside and 27 is not inside. However, because we know 39 and 27, we can actually figure out pretty quickly what that is. It's just the difference between these two. It's 12. And if that's not obvious, then look at it this way. 12 plus 27 would be 39, which is that total distance. So this angle in here is 12 degrees. There's another angle that we can also find easily. We can also find this one. You have to remember from geometry, we have something horizontal, so those lines are parallel. These are alternate interior angles, so that's 27 degrees. Let's try to set up the law of sines. Remember, I'm always going to start by writing that which I'm trying to find. So I'm going to start with x, put that over sine of the opposite angle, which is 12. That equals 1,200 divided by sine of the opposite angle, which is 27. I'm going to multiply up the sine 12. And it's calculator time, so let's go right to it. So 1,200 sine 12 divide by sine 27. Oops. Sine 27. And there it is. 549.55. I'm going to round it to 3 digits. So x equals 550 feet. Always be methodical drawing your pictures on these. That's typically the hardest part, guys. Laws of sines and cosines. Cosines is next. Laws of sines and cosines, they're not super hard. The challenge is usually in the fact that we have an ambiguous case or that the drawings can be kind of tricky. So just pay really close attention when you draw those, and you should be successful on these. Let's do one more. And we are probably to the point now where it would make sense for you to try this one on your own if you feel you're ready for it. All right, we're at summer camp. The counselors want to know how far it is from the camping area. Here's the camping area. To the supply shed, so they know how far they're paddling each day. I guess they're paddling a canoe across the lake here. They hire a surveyor. He places surveying stakes at the camping area, the supply shed, and at another spot just off the lake. That's over here. They measure an angle of 126 degrees at the camping area. I think I'll label that in here. 126 degrees at the camping area. And an angle of 24 degrees at the supply area. So there's an angle of 24 degrees. How far is the supply area from the camping area? All right, pause the video and try it. Hit play when you're ready. At first glance, it seems like maybe there's not enough information because as I go to set up law of sines, I go x divided by sine of the opposite angle, and we don't have the opposite angle. However, we just remember that every triangle has 180 degrees in it. So 180 minus 24 minus 126 should do it. And there it is, 30 degrees. So this angle down here is 30 degrees. So that's just going to be sine of 30. And that's going to equal 326 feet over sine of the thing opposite from 326, which is 24 degrees. Multiply up the sine 30. And this should feel very similar to everything we've done so far. Hopefully you got this one right as you did it on your own. So 326 sine 30 divide by sine 24. And here we go. They are paddling approximately 400 feet. 400, let's round it. Let's go 401. So x equals 401 feet. And does that make sense? Could you paddle that far? Does that look right in the diagram? It does. We should feel pretty confident in that. All right, let's switch gears just a little bit, and we're going to talk about area of a triangle. So here's a question. Do you know how to find the area of a triangle? What I'd expect you to remember from geometry class is that it's either base times height divided by 2, or for today's lesson, I'm going to write it as 1/2 base times height. Now, that worked really well when you had a picture like this. If you had like a 3, 4, 5 triangle, because you could say, do I know what the base is? Yep, it's 3. Do I know what the height is? Yep, it's 4. All right, off to the races I go. It doesn't work quite as well in an example like this. Let's look at why. If I have 3, 4, and 6, because I say, hey, do I know what the base is? Yeah, it's 3. Do I know what the height is? Not exactly. I really don't, okay? So if it's not a right triangle, this gets a little bit tricky. The height comes down from here somewhere. So let's look at an alternate way to understand this, because it would be nice if we had a way of finding the area of any triangle. Consider a triangle that looks like this. Some general arbitrary obtuse triangle. And I'm going to call this big C, and let's call this big B, and let's call that big A. There's no rhyme or reason to this, by the way, it's just what I'm calling them, which means this is little c, and this is little a, and this is little b. And we're going to remember that we're talking about 1/2 base times height. So if I wanted to find the area, I'd do 1/2, and I'd ask, do I know the base? Yeah, I do, it's little a. And I'd say, hey, do I know the height? No, I don't. It's not clear because I don't have a right triangle, but what I could do is I could add in this little section right here, although I want to make that part dotted, so give me just a second to undo, because I don't want you to think that's part of the main triangle. So I could draw in the height like that, and I would probably call it h. And then the question would be, do I have a way of finding h? Well, what I want you to notice, looking at just this large right triangle here, we can actually set up a sine equation. I'm talking like geometry-style sine, SOHCAHTOA type. Remember, SOHCAHTOA would say that's opposite, which we now know is h, over hypotenuse. The hypotenuse on this big triangle here is b. So it'd be h over b. I can multiply the b up to there. So an expression for the height is b sine c. So instead of the height, I can write b sine c. And guys, that's the area formula for any Euclidean triangle. Okay, so you're going to want to write that down somewhere. Here's the part that's important that you understand, though. It's not about the a's and the b's and the c's. That's not really that important because there's nothing magical about why that's a or b or c. But what you do need to understand is that if I think about where a and b are, so there's side length b and there's side length a, where is c in relation to that? It is the included side. Now, when I taught this in class, some of my students said it's the angle that's surrounded by sides. Yeah, I mean, that works. It is. It absolutely is. C is in the middle here. It's surrounded by known sides. And so therefore we can find the area. Let's look at an example of how to apply this. Okay, and here it is. What I want to do, I want to draw a picture to make sure that that context is met, that it's two sides and the included angle, or the angle that's formed between them. So I'm going to draw out the picture, arbitrarily calling these A, B, and C, and then let's label them up. So if little b is 5, this over here is 5, and big angle C is 111, and little a is 3. So I can see that I have my two sides here and the angle formed between them, which we call the included angle. So absolutely I can find the area of this triangle. It's 1/2 AB sine, oops, that was an ugly 111. 111, 1/2 AB sine C. And from there, I'm not going to do anything fancy. I'm just going to go to the calculator. I'm going to do 0.5 because it's easier to type in, times 3, times 5, times sine 111, enter, 7.00 units squared. Okay, that's the area. So guys, pretty darn straightforward, I think. Let's do one that's a little bit more interesting. Okay, let's do a real estate example. So let's say you own a triangular piece of land and you're going to try to sell that thing for $1.5 million because it's waterfront and it's nice. We want to know to the nearest dollar what is the cost of land per square yard. First of all, we got to figure out why is this an area question, because the word area is not given. The giveaway is in the question, per square yard. Square yard is a unit of area. So this is going to be an area question. Okay, next thing we need to do is we need to look at the illustration and say, do we think that we can apply what we just learned to this? So I have 100 right here, I have 95, I have 250. So how is it that we're able to apply the formula we just used? Because we would need angle A in order to do this calculation. Let's see if we can find angle A. I think I'll do this first. I notice that 100 is across from angle B, so let's see if I can find B. Sine of angle B over 100 would be equal to sine of 95 over 250. I can multiply the 100 up, and the only thing you have to remember now, y'all, is that you need to type in sine inverse. Now, I don't actually write the math down when I do this. I just remember to go over and hit sine inverse before I get started, and then I remember to put in a fraction in the parentheses, and then 100 sine 95 on top. And in the denominator, I'm going to go with 250. Oops, I think I hit 2 for some reason. So 250. And let's see what that is. 23.5. So we just found big B is 23.5. And we recall that a triangle has an interior angle sum of 180. So back to my calculator I go. So 180 minus 23.5 minus 95. That'll find that missing angle, the one that we needed. So that's 61.5. So you see how now we have the angle that's included between the sides that were given? So now we can use the area formula. So 1/2 A, B, and there's no rhyme or reason to which is which, by the way. They're multiplied, so it doesn't matter. Sine of 61.5. All right, calculator time. So 0.5 times 100 times 250 times, oh, it's not hitting times for some reason. So times 250 times sine of 61.5. All right, 10985.2. What are the units? That'd probably be square yards. Now, what's the answer to this question? What is the cost of land per square yard? Cost per. So what they're saying is take the dollar amount, divide it by this. So I'm going to jump right into the calculation. It's a little sloppy, but it'll work. So I'm going to take that $1.5 million per by dividing square yards. So all I need to do in the calculator for that is 1500000 divided by, and I can go back and steal that answer, pull it in. And so we're paying $136 $136, and looks like that rounds to 55 cents per square yard. That is the unit cost for our land. All right, y'all. That's all for today. We've covered law of sines and how to find the area of any triangle. Hope it was helpful, and we'll see you next time.